Welcome to the course on FPGA based signal processing systems, as we are doing this IIR filter design, and we're knowing the design process, that how to get the analog filter design, and then discretizing it using the transformations. After that, we get the IIR filter coefficients. So once we have these coefficients, we will be developing the Verilog module. So for that, we'll see that how these IIR filters can be modeled using the Verilog. The first example which we took is that module of IIR input. It needs a clock like any other sequential systems. Input reset is required. Also the input signed, the X input, what is to be given to the filter, and the output of the filter. So these are signed, so because we'll be dealing with the signed inputs as well. So after this declaration, the input output declarations, we'll get into the code module. So the X and Y are, X is the intermediate variable which we use, so we defined it reg signed 0 to W is the parameter which is giving the width of the data. So we can define it according to the need here. W, it is 14. X and Y are the variables which are used in the always block. So now always at passage of the clock or passage of reset, that is, this is an asynchronous reset. If reset is 1, then we have to make this 0 0, the X and Y, the value, the variables which needs to be used here are 0 here, and then end. If else, and then case begin, what is the X in should be applied to X. Xn is the input and X is the intermediate variable here, and then Y equal to, next is Y less than or equal to, you can see the non-blocking one, the Y less than or equal to X plus X right shift by 1 plus Y right shift by 2. Now we can identify what are these shifts or arithmetic right shifts. Okay, so this uses, if we use the arithmetic shift, then in the synthesis process you can see that it uses the less logic elements right shift instead of having the division and the multiplications here. So this equation, which is obeyed by this filter or the integrator, here we have chosen this example as lossy integrator, y of n equal to x of n minus 1 plus 3 by 4 y of n minus 1. So if we take this z transform of it, h of z equal to z per minus 1 by 1 by 1 minus 3 by 4 z per minus 1. So from for this particular integrator, where a is 3 by 4, it's a lossy integrator. What is the, how do we develop this? So how we have used this y of n equal to x of n minus 1 plus 3 by 4 y of n minus 1. So here is the x in is assigned to x. So here is this x of n minus 1. Okay, so because this would, when you use a non-blocking, this is assigning the flip-flop, and it takes the old value, plus these two are corresponding to the y of n minus 1. So y of n minus 1 here, and then this is y of n minus 1, and this is also y of n minus 1, because, and we have the here, so the 3 by 4 coefficient, which is going to be the 1 by 2 and plus 1 by 4. So it is 0.5 plus 0.25. So for 0.25, right shift 1 the data, which leads to dividing by 2, and right shift by 2, which leads to divide by 4. So we have used the arithmetic shift. Okay, so arithmetic shift that extends the sign bit as well. So if y is suppose going to be a sign number, then the sign extension is taken care if you use the arithmetic shift. So 0.5 plus 0.25, 0.75. This can be used, this expression can be written in this other form as well. Y less than or equal to x plus y by that right shift of 1 can be written as divide by division sign decimal 2 and plus y by sign decimal 4. So y by 2 by y by 4, y by 2 plus y by 4 also makes the same equation, x plus y right shift by 1 and y right shift by 2, using the arithmetic shifts. So the signed numbers are written signed decimal 2, signed decimal 4. This we can write it straight away, y less than or equal to x plus y by 2 plus y by 4. So this is going to be the other way of writing the same equation. So three ways in which this difference equation of this lossy integrator can be implemented in the Verilog. If we use this division, then it uses more logic elements in the synthesis process. So the shift operators are preferable, so that we can, in the synthesis process, it would use the less logic elements. Okay. So then end. So the always at the passage of the clock, if reset is that, assign this xy 0, else x, assign x input to x, and x is the now getting output y. So summing this equation here, xn minus 1 plus 3 before yn minus 1, the shifts are implemented in this way, and we get y. And now you got the y, and how to take it, assign it to output y. So that is assign y out equal to y. So connect y to the output pins. This is assign statement. So after doing this summation, you get the y value, and then assign that y value to y out in module. So this integrator tested using the stimulus, that is module IIR TB test bench. Inputs are the clock, reset, and the W is 14 here, so it is 15-bit input, X input, and output is also 15 bits, Y out. Okay. And have this instantiate this module of IIR, clock, reset, input and output. This is y dot y out is the local variable here, y out, and x in, or these two, reset and clock. So after that, initialize this values of clock, and then reset, also x input, and wait for some nanoseconds of the global reset to finish. Here generally we use this 100 nanoseconds, or here it's just given as 10 nanoseconds for the simulation. Add stimulus to get the impulse response. So impulse response, in which we have first, how do we give the impulse response? So in #10, that x input is 0, the x input is made 0, there is no input, and reset is 1. So first we made this reset 1, so that this clears this, it gets the values clock and x input, all of them are 0. And then after 10 time units, x in is made 1000. Okay, reset equal to 0. So 1000, the impulse, not a unit impulse, the amplitude is 1000 here, and then reset is made 0 at that time, and rest of the time x in is 0. So this is for the impulse response. And the step response is similarly #10, instead of that, x in is 0 and made reset 1. After 10 time units, x in, the input is 100, step of 100 magnitude, and then reset equal to 0. So this is for the step response, and end. So like have the clock, that is always #10 clock equal to not clock, initial begin, display the x in and y out, and then monitor $time x in and y out. So this is end here in module. So clock, and so this code is commented for the step response, and this is related to the step response. To get the impulse response, this is commented. Now the impulse response of this 1000 delta n. Okay, so give the input here, this is 1000 delta n at some clock edge, so here, and reset is 1 here in this before that, and then reset is made 0. So when reset is 1, this is continuing with the zeros. You can see at when reset is 1, this output is becoming 0 in this region. Okay, so here as well, and clock is 0. The clock edges can be identified like any other we have done in the previous examples as well. Now the input here, the given, and it is stopped at this point and then made 0 overall here, that impulse response here is that 1000. After that you get the output 1750 and so on. Here the impulse response continues giving the numbers 1000 delta n. So there will be word length effects, like word length effects. Then the approximations would also be seen here. We get this response as a impulse. Right now we are not working for this word length fx. And then the input in xin is that input 1000, and then it is made 0. After that point here you can get the impulse response, which is giving the outputs here, y out output. So this is for the impulse response of the lossy integrator. So this gives 755, 62 and so on. So there is no negative number in this, so you get all positive values. So for the step response, same code, same lossy integrator. If we have this, if you can see that it is increasing, that integrator reset 1 in this point, input is 0, after that it is made 100. Okay, so 0, it starts giving the values from starting from this, and it keep increasing, that integrating over here, but because of the word length effect, then it is saturating at 394. Okay, so you can have this maximum value 394 for the step response of this integrator, and it is keep increasing slowly, and here also. So the same thing can be observed here as well in the data, x input and the y out. So that's about the impulse response and the step response of the lossy integrator. But how do we write this simple one line? If we have the delays of equation only yn minus 1, there is a one line after giving the x input to x, okay, that y of n can be obtained. But if we have more delays in the feed forward and feedback paths as well, then the number of lines in this, you have to store the previous values y of n minus 1, and then use it in the next line. So we'll see some examples on that. But here this IIR2 again, if we have the coefficients little, how do we handle the coefficients? Also, if we have only right shift the division examples. So the same example which has little bit of variation in the equation, difference equation, can be seen in this. So input a clock reset as we had defined in the previous example, and assigned x, y are the and w is 14 if you always at passage of the clock or reset. So you can see that flip-flops and the recursive for input and recursive part we are using, that is the delays recorded in the equation of the IIR filters. If reset begin, make them 0, otherwise, so here, yeah, this is make x is 0, y 0 if reset is 1. If it is not 1, then take the input, assign it to x. For example, here I give x equal to y less than or equal to x plus x by 2, x by 4 plus y by 2 plus y by 16. So here you have this, all x are only delayed ones, that this will take the old value of x, right, because of the non-blocking statement. Y is also yn minus 1. So the equation here is this all together, this coefficients divide by 2 divided by 4, and which sums up to be 7 by 4 the coefficient, and then here y of n minus 1 have the coefficient of 9 by 1 by 2 plus 1 by 16, so 9 by 16. So we can use this division blocks for having the coefficients of smaller sizes, smaller ones. So 1 by 2.5 plus 1 by 2, 1 by 4 if it is 0.25, and then 1 by 8, 0.125, and then 1 by 32. So we can sum it up with y, so that y of n minus 1 as small as possible, this can be added in, the coefficient can be added. So and then end, assign y out equal to y, so end module. So this is having just this coefficient, just to show this coefficients can be of this written in this fashion, can be handled at a particular stage of n minus 1, can be added like this, multiple divisions, though it takes the more logic elements. So the our right shifting it, keep on right shifting it, we can get the coefficients done. So now that will be an approximated coefficients anyway, maybe on here with the 0.00, 0.022 and all will be, will be very difficult to put it in this fashion. So the end module, and then have this impulse response of this again. So you have the coefficient which causes the difference in the impulse response, 1750 and 984, and this is the impulse response it goes up and 984, and then it is decaying in this fashion. The output can be seen for the different clocks, and this is 1000. This is the place where the 1000 in magnitude is given to the filter with delta of an impulse response. So this is to just say that how these coefficients can be made, it smaller coefficients can be handled in this program. So this step response, if you see the same thing like here, it is integrating and going and saturating over here. So step is 100, but it is not the filter which is responding to 100, and it's an integrator. So it would, for the step, it would integrate and keep increasing that values and stay over here. After some time, going to then accommodate much of the, because of the word length effects. And then coming to the, so here the just where we had that coefficient. So we had this equation y equal to x plus x by 2 plus x by 4, and this coefficients change, minus y by 2 plus minus y by 16. Okay, so that is leading to negative here. Okay, the impulse response, it's not an integrator, it's not an integrator, so it gives you the coefficient becomes negative, so the impulse response will give the alternate signs negative. So in the same code we have just modified this coefficient to 9 by 16, so it's possible to have this in the IIR filters. So 0, we get the response as 1750. You can see the signed magnitudes can be handled here, minus 984, 553. Alternative signs are negative. Here negative, negative, the response can be seen also. Okay, so this is an impulse response of this particular equation. Okay, so of the filter, or which is having only one delay at the feedback and one in the feed forward. So this case would be just to indicate that the alternative signs, you can, same thing, you would be able to simulate and see the response in the MATLAB as well. So the IIR filter, which is now taking the another example of the integrator, lossy integrator, which is of second order here. Okay, so the IIR filter 2 input clock we have, and the reset is again reset, input xn and y out. So these are the 4 the declarations needed: clock, reset, input and output. After that, I have defined something here, it's assigned x, y, and the ABC are something new in this compared to the previous code, these variables, and parameter w14. So we'll see them, what are these ABCs. So always at passage of the clock or passage of reset, so use this reset and assign this all the variables to 0, ABC and x, y as well. And this is look ahead the lossy integrator, in which we have this equation. So y of n equal to x of n minus 1, 3 by 4 x of n minus 2, 9 by 16 y of n minus 2. So getting the previous one, y of n equal to x of n minus 1 plus 3 by 4 y of n minus 1. Okay, so this is the that first lossy integrator. So you can have this y of n in the y of the second order case. So you can substitute this integrator at the point, and then get the second order equation also. So we can use this y of n in the second order equation, y of n minus 2, and then we can have the second order equation as well. So getting this y of n, assuming that, so just to show the IIR filter which can have the coefficients, more coefficients at the feed forward and feedback also. So you can see this is y of n minus 2, not y of n minus 1, as we have dealt in the previous case. So now in this case, how do we go for the equations? How do we get how do we write those this equation in the Verilog? So x in is x, we assume it, yes, then, and the xn minus 1, which needs to be formed. So we can have this x in xn minus 1 plus 3 by 4 xn minus 2 need to be obtained. So n minus 2, how do we get this xn minus 2? Because if you have 1, you will have, this is xn minus 1. So if you next stage, if you use the x, because of the 1, this would form one flip flop and this would form this another flip flop, right? So this could be going to be 3 by 4, 1 by 2 plus 1 by 4, 3 by 4 xn minus 1 would be the result of this. Store that we are trying to get this 3 by 4 xn minus 2. Okay, so this one we have made 3 by 4 xn minus 1 in the next stage, store it, and then x is that x we have to delay anyway one time. So xn minus, this is x plus xn minus 1, this is the first portion, plus 3 by 4 xn minus 2, which is over here. So a in the x n minus 2, that is x of n minus 2 is, so x plus a would be giving this particular addition. So x of n minus 1 plus 3 by 4 x of n minus 2, because this would be delayed once. Again, this because of the non-blocking, it would take the one more flip flop is added in this stage. So now what about 9 by 16 n minus 2? Okay, so c equals, again we have to make 9 by 16 y of n minus 1. So use it for y by 2 plus y by 16, whatever that's, store it over in c, and then we can have y which is already in a, x plus a, that is going to be b, this particular portion, and then add c, which is 9 by 16 y n minus 1. So when, because of the non-blocking statement, this will be delayed once, so it becomes y of n minus 2. So we have to handle, this is int. Okay, so this is the code for a particular difference equation to be used in this. So x equal to x in, and then identify is there any coefficient for xn minus 1, and then xn minus 2, if you want, that's xn minus 1, then make this, if there is xn minus 2, then that needs to be added separately with this, make them one more statement is required. So this becomes 3 by 4 x of n minus 2. Similarly, for this y of n minus, there is no y of n minus 1. So though it is giving 9 by 16 y of n minus 1, if we can use it, if it is y of n minus 1, then we can here itself use y equal to y by 2 plus y by 16 plus b. Okay, so this needs to be stored again to get y of n minus 2, so plus c. So this is the way in which we have to deal each and every coefficient. If the number of coefficients is less, okay, good, we can go ahead with this. Otherwise, if you have the order of the filter is more than 8 to 10 and so on, so that's better to use the for loop, and I assign the coefficients. If we have the case of the one problem we did in the previous lecture, that's having 8 coefficients in the feed forward path and the feedback path as well. So using the for loop and use flip flops for the feed forward coefficients, that is delays, and then feedback also. So this is to deal with y of n, x of n minus 1 plus 3 by 4 x of n minus 2 plus 9 by 16 y of n minus 2. So after this, assign this y to y out, okay, then give n module. Okay, so there is this is the difference in the code which gives us the equation of this. So if you have y of n minus 3, you will be adding one more line extra, so as this lines will be more and more, depends on the number of delays used. That's obviously the flip flops, d flip flops it is going to be using. So with this, we have this equation and the impulse response, as well as only impulse response we have done 1000 del n for this case, and you can see the clock edges and the reset. It's the same test bench which what I had given is can be used here as well. So but the clock period is made here 20, so because two clock periods more than that. So we have this 50 and 100. So this is one clock period, and then this is another clock period, so on. So we have this 20 time units here, and the x input is 1000. Okay, each reset become 1 over certain point, and then x input is made 1000 at this clock edge, and then half of time period of the clock it is existing, after that it is made 0. So it's a very short pulse of 1000, and then the resultant output of y out is 0 here, and then it goes to 1000 here. You can see 750, 562, and so on, coming back to 0. This is also a lossy integrator. If you see the previous, this is look ahead one. So if we had this x of n minus 1 plus 3 by 4 x y of n minus 1, that was the first, the lossy one. So here now the look ahead order 2, the lossy integrator 2, so the 9 by 16 y of n minus 2. So this would also give the same response as this lossy integrator. You can verify that using those response as well. So here is the difference we need to have. How do we, especially how do we handle this coefficients? So these coefficients can be obtained from the design, that is given the specification. First get the analog filter. If the specification is an analog, the analog filter either Butterworth or Chebyshev filter, and from that use the discretization process, or in either impulse invariance or the bilinear transform as we discussed, and get the h of z, that is the transfer function of this IIR filter. After from that filter you can get the difference equation like this. If you go for the inverse z transform, when doing this process, the sampling time needs to be taken care in the design. So you get this difference equations. After getting this difference equation, and you can develop the Verilog modules like this. But in the simulator you can verify this 15 bits or outputs like that in the board. If FPGA board, if you would like to download this code and then get the output, so that it's 16 bits, you need the output pins for it. That output pins each are we can use this output to be connected to the D2A, and then view this signal in the DSO. So use through the D2A converter. So the similar way, the input to the filter can be given through the ADC, digitized input. That suppose this an impulse input or the step input, or the signal which is to be processed through the IIR filter, or input signal with noise, or the band of frequencies from which needs to be removed from that. That can be given through the ADC, and then the digital signal is communicated through the FPGA, and there is a communication protocols, and then after processing it in FPGA, then the digital signal again, this outputs can be given to D2A, and the analog output can be viewed in the DSO. So this is how the complete process of analog signal getting into the filtered by digital filter, and then getting back to the analog domain as in the real world. So these filters can be used in any of the systems which can be of continuous time systems or the discrete time systems. So but the filter design is in digital, so which can be in the chip of the FPGA. So with this we complete this in infinite impulse response filters, and also the IIR filters, and we'll be dealing with DFT, FFTs and other things in the coming lecture. Thank you.